Hello everyone and welcome to Math Chat with Nasir. So far we have completed 4 lectures in our linear algebra course which we have started a few years ago. Lecture 1 covers vector spaces, Lecture 2 gives an introduction to subspaces, Lecture 3 focuses on spans, basis and dimension of vector spaces, linear combinations and linear independence. Lecture 4 covers solving systems of linear equations. If you haven't already watched these lectures yet, I highly recommend you watch them before continuing. Originally, we planned our 5th lecture to be on linear transformations. However, we have made a slight change in the sequence. Our 5th lecture, which is the current lecture, focuses on algebra of matrices. We will cover linear transformations in the next lecture, which will be the 6th lecture of this course on linear algebra. Let's begin today's lecture without any further delay. Before we move on, I would like to request you to subscribe to the channel if you haven't already. Also, please share the channel with your friends and encourage them to subscribe. Your support helps us create more educational content. Let's get started. We start with the definition of a matrix. A matrix over a field F is a rectangular arrangement of numbers called the elements or entries of the matrix. A general format of a matrix is A11, A12, A13 and up to AMN. The elements are arranged in rows and columns. The matrix A has m rows and n columns. The number of rows and the number of columns of a matrix is called its order, and we write the order of a matrix as order A equal m cross n. The elements of a matrix come from a field. If you have no idea what a field is, I recommend watching the first lecture of this course. Basically, a field is a set along with the definitions of operations of addition and multiplication of different elements. How elements will be added or multiplied is defined by the underlying field. Let us look at some examples of matrices. The matrix B has 2 rows and 3 columns. The matrix C has 3 rows and 2 columns, and the matrix D has 2 rows and 2 columns. We write order of B equal 2 cross 3, order of C equal to 3 cross 2, and order of D equal to 2 cross 2. A matrix that has the same number of rows and columns is called a square matrix. Otherwise, it is called a rectangular matrix. Here D is a square matrix while both B and C are rectangular matrices. Let us see how a matrix is represented. A matrix of order n symbolically is written as Aij, where the order of the matrix is written alongside. The symbol Aij represents the element of the matrix at ith row and jth column. The first subscript represents the row number and the second subscript represents the column number. So this matrix essentially represents an m cross n matrix A. Before we continue, you should also familiarize yourself with the summation notation represented by the Greek letter sigma. We can compactly represent sum of large sequences with summation notation. For example, sum of the series from B1 to Bn can be represented as summation k's from 1 to n bi. Here small k is just an index. We can safely use I instead of k. This represents the sum of the same sequence B1 to Bn. We can write sum of a sequence from 5 to 1000 in all integers as summation k is from 5 to 1000 k. Likewise, the sum A1 B1 plus A2 B2 plus A3 B3 up to An Bn can be written as summation I is from 1 to n Ai Bi. Matrix addition. Let us see how we can add two matrices. First, you should remember that not all pairs of matrices are compatible for matrix addition. Two matrices are consistent for matrix addition if they have the same number of rows and same number of columns. It means two matrices can only be added if they have the same order. Matrix addition for two matrices having different orders is not defined. Suppose we have these six matrices A, B, C, D, E, and F. The matrices B and D have the same order. They can be added together. Likewise, the matrices C and E also have the same number of rows and the same number of columns. They are also consistent for matrix addition. However, we cannot add A and F or B and C or D and F because these pairs have different orders. Let us see what is the exact procedure to add two matrices of the same order. Suppose matrices A and B have the same order and the matrix C represents their addition. The element at row I and column J of the sum A plus B, which we represent as Cij, can be calculated by adding the elements of A and B at the same row and same column. So the matrix addition is done by adding elements at corresponding rows and columns. Another matrix operation is scalar multiplication. Scalar multiplication is basically the multiplication of a single element from the field to the whole matrix. So if K is a scalar and A is a matrix, then the scalar multiplication of A with K is defined as the multiplication of K with all the elements of the matrix A. If A is a 2 cross 2 matrix, then we can find 7 times A as this matrix. Let us look at some more examples of matrix addition. Here A and B are two matrices of the same order, 2 cross 3, 2 rows and 3 columns. We can find A plus B by adding corresponding elements. We add 3 and 6, 5 and 2 and so on. The scalar multiplication of A with 3. Just multiply 3 with every element of the matrix A. If we need to perform combined operation of scalar multiplication and addition such as 2A plus 3B, first we will perform scalar multiplication and then perform the matrix addition. Matrix subtraction. We can subtract matrix A from B by adding matrix with scalar multiple of B with minus 1. Now let us look at some important properties of matrix addition. Suppose A, B and C are three matrices of the same order so that they are compatible for matrix addition. Then first property, A plus B is equal to B plus A. This is called the commutativity of addition. Order of addition does not matter. Matrix addition is commutative. Second property, there exists a matrix represented by the capital letter O called the additive identity or the zero matrix, such that if we add it to any matrix, the same matrix is obtained. This is most widely known as the zero matrix. Third property, for each matrix there exists another matrix represented by minus A such that adding minus A to A results in the zero matrix. The matrix minus A is called the additive inverse of A. Actually, A and minus A are additive inverses of each other. The last property is the associativity of addition. The matrix addition is associative. Let us prove these properties formally. Suppose A is equal to Aij, B is equal to Bij and C is equal to Cij. the element at row I and column j of the matrix A plus B is the sum of the corresponding elements of the matrices A and B, which is Aij plus Bij. Now we can write Aij plus Bij as Bij plus Aij, because Aij and Bij all entries belong to the field F and addition is commutative in the field. Now look at the right hand side, which is Bij plus Aij is the element at row I and column j of the addition B plus A. Since this is true for all ij, therefore we have A plus B equal to B plus A. Second property, the existence of additive identity. Suppose O is equal to the M cross N matrix with all zeros, where 0 is the additive identity element of the field F. Ith jth element at row I and column j of A plus O is equal to Aij plus 0, which is again equal to Aij. Why? Because Aij and 0 both belong to the field F and 0 is the additive identity of the field. Since this is true for all ij, we have A plus 0 matrix equal to A. Third property, the existence of the additive inverse. Let minus A be equal to the matrix A with inverted sign of each element of the matrix A. Then we can show that adding A to minus A results in 0 matrix. The same method. We calculate element at row I and column j of A plus minus A. We get Aij plus minus Aij, which is equal to 0. Again, this is from the property of the field F. From this we conclude that A plus minus A is equal to 0 matrix. Fourth and the last property, the associativity of the matrix addition. Again, we calculate ith, jth entry of A plus B plus C, which is equal to Aij plus Bij brackets plus Cij. Using the associative property of the addition for field, we have Aij plus Bij plus Cij bracketed. From this we have our associative property for matrix addition. Our next topic is matrix multiplication. Let us try to multiply two matrices element by element. 2 is multiplied with 1, 3 with 7 and so on. So our resultant matrix obtained by multiplication of A with B is 2, 21, 0, 10, 18 and 8. But this is not how matrix multiplication works. Matrix addition is performed element by element, means we add corresponding elements. But when we say multiplication of two matrices, the method is different from addition. Matrix multiplication is not performed element by element. Even in this case, A and B have the same order, but they are not consistent for matrix multiplication. They cannot be multiplied together. So how exactly can we check if two matrices are consistent for matrix multiplication? If the number of columns of the left matrix is equal to the number of rows of the right matrix, the matrices can be multiplied. They are consistent for multiplication. If A has order 2 cross 3 and B has order 3 cross 5, matrix multiplication AB is compatible, but BA is not compatible. So we cannot perform B on the left side and A on the right side. Yes, order does matter in matrix multiplication. If a matrix A has 5 rows and 4 columns and matrix B has 2 rows and 5 columns, matrix multiplication BA can be performed, but the matrix multiplication AB cannot be performed. Suppose a matrix A has order of m rows and n columns and another matrix B has n rows and p columns. then the matrix obtained by matrix multiplication AB has m rows and p columns. It has the same number of rows as that of the left matrix and the same number of columns as that of the right matrix. So again, how exactly can we perform matrix multiplication? Again, suppose matrix A has m rows and n columns and matrix B has n rows and p columns. The number of columns of A is n and the number of rows of B is also n. So we can perform the matrix multiplication AB, A on the left side. Let us denote the element at row I and column j of the multiplication matrix as AB subscript ij. This single element is calculated using this summation. I can be index of the any row and j can be index of the any column of the resultant matrix. Let us expand this summation. We see that these elements combined is the ith row of the matrix A and these elements is the jth column of the matrix B. So a single element at row I and column j is obtained by multiplying ith row and jth column element wise, then adding them together. Let us see some examples of matrix multiplication. We have two matrices A and B. The number of columns of A and the number of rows of B are equal. Both are equal to 3. So we can multiply A with B. The first element is obtained by multiplying the first row with the first column and then adding them together. For second element, we multiply first row of A with the second column of B and first row with the third column for third element. Likewise, we multiply second row with the first column to calculate first element of the second row and so on. The resultant matrix has two rows which is equal to the number of rows of A and has three columns which is equal to the number of columns of B. Can we perform the matrix multiplication BA in this case? The number of columns of B is 3 and the number of rows of A is 2. They are not equal. Therefore, the matrix multiplication BA cannot be performed. We now look at when it is possible to perform both AB and BA. Suppose A and B are two matrices with respective orders of M1 cross N1 and M2 cross N2. The matrix multiplication AB is consistent, means we can perform this multiplication if the number of columns of A is equal to the number of rows of B. And the matrix multiplication BA is consistent if the number of columns of B is equal to the number of rows of A. So we have N1 equal to M2, say both N1 and M2 equal to N. Secondly, N2 should be equal to M1. Suppose both M1 and N2 is represented by M. From this we see that both AB and BA are compatible for matrix multiplication if one matrix has the order of M cross N and the other matrix has order of N cross M. For example, A has 2 rows and 3 columns and B has 3 rows and 2 columns. In this case, both AB and BA are compatible for matrix multiplication. If A has order of 9 cross 5 and B has order of 5 cross 9, or A has order of 7 cross 3 and B has order of 3 cross 7, or maybe A has order of 4 cross 4 and B also has order of 4 cross 4. In all these 4 cases, matrix multiplications AB as well as BA can be performed. One important thing to keep in mind is that even if AB and BA both can be performed sometimes. Still, AB is not necessarily equal to BA. We can see it with an example. Matrix multiplications AB and BA come out to be different. So, contrary to the matrix addition, matrix multiplication is not commutative. Properties of matrix multiplication. First, AB is not equal to BA, matrix multiplication is non-commutative. Second, matrix multiplication is associative. Third, matrix multiplication is left distributive over addition. It is also right distributive over addition. Proving first property is straightforward. In fact, we have already proven the first property. We have already shown a counter example that matrix multiplication is non-commutative. It is also obvious that when both AB and B are compatible for matrix multiplication, that is the order of A is m cross n and the order of B is n cross m. From this we see that the order of the resultant matrix AB is m cross m, whereas the order of BA is n cross m. Since the order of the two matrices are different, the matrices are also different. So, matrix multiplication is not commutative. Second property, the associativity of the matrix multiplication. Suppose A has order m cross n, B has order n cross p, and C has order n cross r. First, we calculate the element at row I and column k of the multiplication AB. Suppose it is represented by dik. Likewise, we calculate the element at row j and column L of the multiplication matrix BC. We represent it by GJL. So the matrix AB is equal to dik and it has order of m cross p, and the matrix BC is equal to GJL and it has order of n cross r. Let us now calculate the element at row I and column L of the matrix AB multiplied with C. It is summation k is from 1 to p dik ckl. Replace dik with the summation j is from 1 to n aij bjk. Now we can take C, K, L inside the summation, and using the distributive law of elements of the field, we can change the order of multiplication of these three elements. The order of the summation can also be changed without affecting the result. Now we see that the element aij does not depend on the summation index k. Therefore, we can take it out of the second summation. Now compare these two summations. It is GJL, the element of the matrix multiplication BC. Now look at this summation. It looks like it is calculating the element at row I and column L of the matrix multiplication of A with BC. Since this is true for all I and L, we conclude that AB into C is equal to A into BC. Let us prove third property, left distributive law of multiplication over addition. Suppose A and B have respective orders of m cross n and n cross p. And suppose C also has the order n cross p, so that the matrix addition B plus C is consistent. Let us first calculate the element at row I and column K of the matrix multiplications AB and AC. Now we add B and C. This is the element at row J and column K. Now we multiply A with B plus C and calculate the element at row I and column K. It is equal to the summation j is from 1 to n aij hjk. Replace hjk with bjk plus cjk. Now using the distributive property of multiplication over addition for the elements of the field, we can arrange the elements A, B and C like this. The first summation looks like the matrix multiplication AB and the second summation looks like AC. This is true for all I and K. We have our desired result. You can prove the right distributive law yourself on the same lines. We will now discuss another operation on matrices which is called the transpose of a matrix. The transpose of a matrix A is denoted as A superscript T. Contrary to the addition and multiplication, which are binary operations, which means they are performed on two matrices, transpose of a matrix is a unary operation. It is performed on a single matrix. If the matrix A has m rows and n columns, its transpose will have n rows and m columns. The number of rows and the number of columns will be interchanged. Here is how we calculate element at row J and column I of the transpose of A. It is equal to element at row I and column J of the matrix A. For example, we have A equal to this matrix having order of 2 rows and 2 columns. It is A11, A12, A13. And the second row's elements are A21, A22 and A23. Let us find the elements of the transpose of A. Element at row 1 and column 1 is A11, which is 2. Element at row 1, column 2 in A transpose is equal to A21, which is 6. Likewise, element at row 2, column 1 is equal to A12, which is 9. At row 2, column 2 is A22, 3. We calculate the elements of the last row as the last column of A. Just notice that the first column of the matrix A has become the first row of the A transpose. The second column of A has become the second row of A transpose, and the third column of A has become the third row of A transpose. So changing rows to columns or equivalently columns to rows results in the transpose of a matrix. Let us discuss important properties of matrix transpose. First, transpose of A plus B is equal to the transpose of A plus the transpose of B. Second, transpose of A is equal to A. Third, transpose of scalar multiple of the matrix A is equal to the scalar multiple of the transpose of A. And the fourth property is transpose of the matrix multiplication AB is equal to B transpose multiplied by A transpose. The order is changed if transpose is taken first. Let us prove each of these properties. First property, A plus B transpose is equal to A transpose plus B transpose. Suppose A and B are two matrices of the same order, m cross n, m rows and n columns. Then by definition of addition of two matrices, the entry at row I and column J of A plus B is obtained by adding the corresponding entries in the two matrices Aij plus Bij. Now by definition of the transpose, the element at row j and the column I of A plus B transpose is equal to the element at row I and column j of A plus B, which is equal to Aij plus Bij. But Aij is equal to the element at row j and column I of A transpose. Likewise, Bij is equal to the element at row j and column I of B transpose. Since this is true for all values of I and j, therefore we have A plus B whole transpose equal to A transpose plus B transpose. Second property, transpose of A is equal to A. Again, suppose A is an M cross N matrix. Ji element of A transpose is equal to Aij. Now calculate element at row I and column j of transpose of A, which by definition is equal to the element at row j and column I of the A transpose. But we have already seen that this is equal to Aij. This implies that A transpose is equal to A. I leave the third property for you to prove it. Let us look at the proof of the fourth property, which is AB whole transpose is equal to B transpose into A transpose. Suppose A is an M cross N matrix with elements Aij and B is an N cross P matrix with the elements B, J, K. The element at row I and column K of the product matrix AB is equal to the summation j is from 1 to n Aij, Bjk. Now the element at row K and column I of the AB matrix whole transpose is by definition equal to ABIK, which we have already seen that is equal to this summation. We can write Aij as the A transpose Ji and Bjk as B transpose Kj. We can switch the order of the elements inside the summation because these elements are from the field and multiplication in the field is commutative. Now look closely at this summation. This is the element at row K and column I of the matrix multiplication B transpose into A transpose. So element at row K and column I of AB whole transpose is equal to the element at same location of the product B transpose into A transpose. Since this is true for all values of I and K, we have our desired result that AB whole transpose is equal to B transpose into A transpose. A few more important concepts about matrices. A matrix is called a square matrix if its number of rows and the number of columns are equal. For example, A has 2 rows and 2 columns and B has 3 rows and 3 columns. So A and B both are square matrices. A is a square matrix and B is also a square matrix. Trace of a matrix. Suppose A is a square matrix, then the trace of A is defined as the summation I from 1 to n I. It is simply the sum of the diagonal elements of the matrix. In these two examples, trace of A is 2 plus 9 equal to 11 and trace of B is equal to 5 minus 2 plus 9 which is equal to 12. You should note that the trace of a matrix is applicable for square matrices only. Another concept is the zero matrix, which we have already seen when we discussed matrix addition. A matrix having all of its entries equal to 0 is called a zero matrix. A zero matrix is the additive identity for matrices. Diagonal matrix, a matrix A equal Aij. Again, it should be a square matrix. It is called a diagonal matrix if Aij is equal to 0 for all I not equal to j. It means that whenever the element is not on the main diagonal, it is 0. The non-diagonal entries are 0. So these types of square matrices are called diagonal matrices. Let us recap a few ideas to build a background for the new concepts. We have already discussed that zero matrix acts as the additive identity. The set of real numbers also has the additive identity, which is the number 0. If there is an additive identity, there is a multiplicative identity as well. For set of real numbers, 1 is the multiplicative identity because multiplying 1 with any uh, real number x results in the same real number x. So what is the multiplicative identity for set of square matrices? What matrix should we place at this question mark so that the product results in the same matrix A? This is the definition of the multiplicative identity. The multiplicative identity is denoted by the capital letter I. Suppose A is equal to Aij is a square matrix of order n rows and n columns. Then the matrix I subscript n is for the order of the matrix, having entries 0 at non-diagonal positions and all ones at the diagonal positions. So In is a diagonal matrix with entries at the diagonal equal to 1. This matrix is the identity matrix of order n rows and n columns. Identity matrix of order 2 is 1 0 0 1. Identity matrix of order 3 is 1 0 0 0 1 0 and 0 0 1. We can write ith jth element of the identity matrix as delta ij. This symbol is called Kronecker delta. The definition of the Kronecker delta is that it is equal to 1 if I is equal to j and equal to 0 if I is not equal to j. So we can write identity matrix as delta ij. This identity matrix is the multiplicative identity for matrices of order n cross m. Means AI is equal to IA is equal to A. Let us prove it formally. Suppose A is equal to Aij having n rows and n columns. The element at row I and column j of the multiplication AI is equal to the summation k is from 1 to n aik delta kj. If we expand the summation, we have some of these elements. Look at this. Delta will only be 1 when the both indices are j. From this we obtain the summation equal to aij. Ith jth entry of the product ai is the element aij. From this it implies that ai is equal to a. On the same lines, we can prove that the product I into A is equal to the matrix A. So I is the multiplicative identity for matrices. Additive identity is widely referred to as the zero matrix whereas the multiplicate entity is referred to as the identity matrix. We will also adopt this convention. When we say identity matrix, it means we are referring to the multiplicative identity. Secondly, zero matrix can have any order, square or rectangular. On the other hand, an identity matrix is always a square matrix. Let us now discuss the additive and multiplicative inverses. If x is a real number, then minus x is the additive inverse of x because adding them together results in the zero. In fact, x and minus x are additive inverses of each other. Two real numbers x and y are called additive inverse of each other if x and y is equal to 0. For example, 2 and minus 2 are additive inverses of each other. 5 and minus 5 are additive inverses of each other. 8 and minus 8 and so on. Every real number has its own unique additive inverse. For matrices, every matrix A has its additive inverse, which is the matrix minus A. For example, A and minus A, these are additive inverses of each other. So, two matrices A and B are additive inverse of each other if A plus B is equal to 0 matrix of the same order. Let us discuss the multiplicative inverses. If x is a real number, 1 over x is the multiplicative inverse of x because the product of x and 1 over x is equal to 1, the multiplicative identity. So, two elements x and y are called multiplicative inverse of each other if xy is equal to yx is equal to 1, the multiplicative identity. Every real number has its unique multiplicative inverse, except the number 0. 0 does not have a multiplicative inverse. What about matrices? Two matrices A and B are called multiplicative inverse of each other if AB is equal to BA is equal to the identity matrix. As the real number 0 does not have its multiplicative inverse, the 0 matrix does not have its multiplicative inverse as well. But 0 matrix is not the only matrix which does not have an inverse. For set of real numbers, only the real number 0 does not have inverse. But for set of matrices, there are many matrices for which multiplicative inverse does not exist. Let us compare side by side. Only one real number does not have its multiplicative inverse. It is the number 0. For set of matrices of order n, there are many matrices, in fact infinite number of matrices, which does not have an inverse. 0 is one of them. Matrices which do not have an inverse are called singular matrices, and the matrices which do have multiplicative inverse are called non-singular matrices. They are also called invertible because multiplicative inverse exists for these matrices. So, matrix A is called singular if it does not have an inverse, otherwise it is called non-singular. When we simply say inverse of a matrix, we will always mean the multiplicative inverse. So, a matrix is non-singular or invertible if there exists a matrix B such that AB is equal to BA is equal to the identity matrix. The matrix B is called the inverse of A and is written as A power minus 1. So far, we have just discussed what an inverse is, but we have not yet outlined any method to find inverse of an invertible matrix A. Let us define elementary operations on a matrix. These operations are used to find inverse of a non-singular matrix. There are three types of elementary operations on a matrix. First, interchanging any two rows of a matrix. Second, multiplying any row of a matrix with a constant. Third elementary operation is adding a constant multiple of a row to another row of a matrix. For example, we have this matrix having 3 rows and 4 columns. We interchange first and the third row. This is the first type of elementary operation. It is denoted as R1 double arrow R3. Second type of elementary operation, we multiply the second row with 4. It is denoted as 4 times R2. Third type of elementary operation, we add 2 times the third row to the second row. The third row will remain unchanged, only the second row will change. A related concept is the concept of elementary matrix. A matrix obtained by performing any one of these elementary operations on the identity matrix is called an elementary matrix. For example, we have an identity matrix. We interchange second and the third row and we obtain elementary matrix of type 1. Multiply first row with the constant, say 5, we obtain elementary matrix of type 2. Likewise, if we add 6 times the first row to the second row, we obtain elementary matrix of type 3. We will now discuss an important result about elementary operations. We state this theorem about elementary operations without proof. I invite you to try to outline a general proof of this theorem. The theorem states that if A is a matrix of order m cross n, then an elementary operation of any type can be performed on A by multiplying with A the elementary matrix of the same type, like E, A. We discuss this theorem with an example. Here is a matrix A whose order is 4 rows and 3 columns. First, we perform elementary operation of type 1 on A directly by interchanging the row 2 and row 3. Now, let us create an elementary matrix of the same type by interchanging row 2 and row 3 of the identity matrix. If we multiply E with A, first row first column, first row second column, and so on, we get this matrix, which is equal to the matrix already obtained. Now let us look at the second type of elementary operation. We multiply second row of A with 5, then create an elementary matrix of the same type and multiply it with A. Get the same matrix as in the case of applying elementary operation directly on A. Third type of elementary operation, change first row of A by adding into it 5 times the second row. We create the same type of elementary matrix again by performing the same operation on the identity matrix. Now let us multiply E with A. We can see that we again got the same 2 matrices. In these 3 examples, we have described that an elementary operation can be performed using matrix multiplication instead of performing the operation directly. You may think that why the other way around and use slightly complex procedure of elementary matrix and matrix multiplication when we can easily apply elementary operations directly on A. This will become clear when we discuss the method to find the inverse of a matrix. So let us go ahead and discuss how to find inverse of a non-singular square matrix using elementary operations. Suppose we apply k elementary operations sequentially on a matrix A. We write the operations from right to left. So OOP1 will be applied first and so on up to OOP k. All of these k operations are one of the three types of elementary operations. As we have already discussed, we can perform these elementary operations using appropriate elementary operations E1, E2, E3 and so on up to Ek. Because matrix multiplication is associative. The same effect of all the k elementary operations on A can be achieved by first multiplying all the elementary matrices together and then multiplying E with A. After E is multiplied to A, we obtain another matrix which will be as if we have performed these k elementary operations on A sequentially. This is an important result. Now please pay attention. We perform elementary operations on A in such a way that we obtain identity matrix at the end. These n operations can also be performed using the elementary matrices so that EA is equal to I. Now this looks like familiar. It is the definition of the inverse of the matrix A. Here E is the inverse of A. Let us demonstrate this method using a small matrix of order 2 cross 2. We write the matrix A for which we need to find the inverse on the left side, write the identity matrix side by side. Now we perform same elementary operations on both matrices. The target is to make our first matrix equal to the identity matrix. First operation, multiply first row by 1 over 2. Second operation, subtract first row from the second row, R2 minus R1, so that the first element of the second row should become 0. Note that our target is to transform the first matrix to the identity matrix, and we don't care what the matrix on the right side will become. We just perform the same elementary operation on the second matrix as well. Third elementary operation, multiply second row with 2 by 7 so that the second element of the second row becomes 1. Now we subtract 3 by 2 times the second row from the first row. R1 equal R1 minus 3 by 2 R2. Now we have converted the original matrix to an identity matrix. This matrix is the inverse of the original matrix A. We can verify this by multiplying them. Multiply both matrices, first element 10 by 7 minus 3 by 7, second element minus 6 by 7 plus 6 by 7, first element of the second row 5 by 7 minus 5 by 7, and second element of the second row minus 3 by 7 plus 10 by 7. This is equal to the identity matrix. You can try yourself and change the order of multiplication. Multiply A minus 1 to A. It will also be equal to an identity matrix. So this is a very beautiful method for finding inverse of a matrix. A more compact method to find inverse is to write the original matrix and the identity matrix together with a bar in between them. Now perform elementary operations on this whole matrix so that the matrix on the left side becomes an identity matrix at the end. Whatever will remain at the end on the right side will be the inverse of the matrix. Properties of inverse of a matrix. First, Inverse of a matrix is unique. Second, inverse of A is again equal to A. Third, inverse of transpose of A is equal to the transpose of the inverse of A. Fourth, inverse of the matrix multiplication AB is equal to B inverse into A inverse. Fifth, inverse of constant multiple of A, which is Ka, is equal to 1 by K into inverse of A. Sixth, inverse of the identity matrix is the identity matrix itself. We will discuss proof of each of these properties. Let us first recall the definition of the inverse of a matrix X. Y is the inverse of X if xy is equal to yx is equal to the identity matrix. First property, inverse is unique. Suppose B and C are two inverses of a non-singular matrix A. Then by definition of inverse, AB is equal to BA is equal to the identity matrix and AC is equal to CA is equal to the identity matrix. We can write BI equal to B into AC because C is equal to the identity matrix. By associativity of multiplication, we have BA into C, but BA again is the identity matrix because B and A are inverses of each other. We get identity matrix into C equal to the matrix C. Since the left hand side is B, we conclude that B is equal to C. Second property, inverse of A is equal to A. Since A inverse into A is equal to the identity matrix, also A into A inverse is equal to the identity matrix. From the definition of the inverse of A is equal to A. Fourth property, AB whole inverse is equal to B inverse into A inverse. Let us multiply AB with B inverse, A inverse. By associativity of multiplication, we can change the order of matrix multiplication. Again, change the order of the multiplication. B into B inverse is equal to the identity matrix. We have A into A inverse, which is again equal to the identity matrix. On the same lines, we can verify that B inverse into A inverse into AB is equal to the identity matrix. Now we have verified this. Imagine AB is X and B inverse A inverse is Y and compare it with the definition of the matrix inverse. We have Y equal to inverse of X or B inverse into A inverse is equal to AB whole inverse. Just change the order and we have our desired result. Third property is inverse of A transpose is equal to the transpose of A inverse. Multiply A transpose with transpose of A inverse. We can write it as A inverse into A whole transpose because AB whole transpose is equal to B transpose into A transpose. A inverse into A is equal to the identity matrix. So we have identity matrix. Likewise, we can verify that transpose of A inverse into A transpose is equal to the identity matrix. From these two equations, we have the desired result that inverse of A transpose is equal to transpose of A inverse. We can also prove the fifth property, which is inverse of K is equal to 1 by K into A inverse. We can verify this by multiplying Ka with 1 over K into A inverse, which is equal to the identity matrix. The sixth property, that the inverse of an identity matrix is the identity matrix itself, is straightforward. Our next topic is also an important part of this lecture, which is the determinant of a matrix. Determinant of a matrix is a function from set of square matrices to the set of the field F. If the field is the set of real numbers, then the determinant of a matrix is a real number. Determinant of a 2 cross 2 matrix, suppose the matrix A has entries A11, A12, A21 and A22. The determinant is equal to A11, A22 minus A12, A21. The determinant of A is denoted as DETAR A mod. It is equal to A11, A22 minus A12, A21. Suppose B is equal to 5, 7, 2, 9, then the determinant of B is equal to 9 into 5, which is 45, minus 7 into 2, which is 14, which is equal to again 31. So 31 is the determinant of the matrix B. You should remember this formula for the determinant of a 2 cross 2 matrix. We will also discuss method to calculate determinant of higher order matrices. But before that, we need to discuss some more related concepts. Let us first discuss what is a minor matrix. Suppose A is a 3 cross 3 matrix. Define M11 as the matrix obtained after deleting first row and the first column of A. M12 is the matrix obtained after removing first row and the second column. M13 is obtained by removing the first row and the third column, and so on. The matrix 2,3 is obtained by removing the second row and the third column of A. In general, Mij is the matrix obtained after removing ith row and jth column of the matrix A. It is called the minor matrix of the element Aij. So this is the minor matrix of the element 2, this is the minor matrix of the element 1, this is the minor matrix of the element 3, and so on. This is the minor matrix of the element 7. In general, there are as many minor matrices as the number of elements of the matrix A. If we calculate determinant of a minor matrix, it is called minor of the corresponding element. Minor without word the matrix A. So minor matrix and minor. Minor is the determinant of the minor matrix. So minor of Aij is the determinant of Mij. Minor of A11 is 2, minor of A12 is 13, minor of A13 is 10, and the minor of A23 is 15. We have already discussed the method to calculate determinant of a matrix of order 2 cross 2. Now we will discuss the more generic method to find the determinant of a matrix of any order. Suppose A is a matrix of order n. The determinant of A is equal to the summation j is from 1 to n minus 1 raised to the power 1 plus j A1j into minor of A1j. We can write the summation in expanded form. We see that these are the elements of the first row of A. Each element is multiplied by its minor and then added and subtracted alternatively together. Suppose A is equal to this matrix, determinant of A is equal to 3 into minor of 3 minus 2 into minor of 2 plus 1 into minor of 1. Here these bars represent the determinant. This is equal to minus 50. So the determinant of A is minus 50. In this case, the summation has been done along row 1. Why is that? In fact, we can use any row or any column to find the determinant. In general, we fix I to have any value from 1 to n, but once it is fixed, it will remain the same. We can also fix any column and expand the summation along the rows. Both methods will result in the same value for the determinant. If a matrix A contains a row with higher number of zeros, then calculating determinant along that row will be easier. For example, here row number 2 has 2 zeros. We can expand determinant along row 2, which comes out to be 36. Let us discuss properties of determinants. First, the determinant of A transpose is equal to the determinant of A. Second, if A has a row or column of zeros, then determinant of A is 0. Third, if A has two identical rows or columns, then the determinant of A is 0. Fourth, if A is a triangular matrix is one which has all zeros above or below the diagonal. So if A is a triangular matrix, then determinant of A is the product of the diagonal elements. Fifth, determinant of the matrix product AB is equal to the product of their respective determinants. Sixth, determinant of A inverse is equal to 1 over the determinant of A. Seventh, A is non-singular or invertible if and only if the determinant of A is non-zero. Now we see the effect of elementary operations on the determinant. We have 3 more properties of determinant related to 3 types of elementary operations. If B is obtained from A by interchanging any 2 rows, then the determinant of B is equal to minus the determinant of A. Ninth property, if B is obtained from A by multiplying any row or column by a constant k, then the determinant of B is equal to k times the determinant of A. The third type of elementary operation has no effect on the determinant. If B is obtained from A by adding a constant multiple of a row or column to another row or column, then the determinant of B will remain the same as the determinant of A. Thank you very much for watching this lecture. If you find this lecture helpful, please like the video and subscribe to the channel. This will help us create more educational videos on computer science, artificial intelligence, machine learning, mathematics and probability theory. Keep watching.